Yeah, pretty good.
Okay, what's up, everybody? I'm Nathan, and this week we're going to be talking about DSi Browser Hacking, which is a project which I've been working on for the last. I started in last summer, and then worked all the way till December, so it's been a long time coming, actually. First up, we'll start with some announcements. Anisha, you want to take the announcements?
Yeah, sure. Stand. The first one is a scavenger hunt with quizzes. It's like next weekend, I believe. Yeah, next Saturday. So it's going to be like a super cool scavenger hunt. We're gonna have like pizza and prizes. If you haven't signed up, we do track signups. So like go to the link. It's in our Discord and it will also be on the slides. But like please sign up for it so we know how many people are coming. Otherwise, you won't have pizza and that's sad. Also, there's an ICSSP meeting this week sometime, I believe. I think this Thursday. At 5 p.m. in 2405. It's a really good scholarship opportunity for people interested in cybersecurity. You like get college paid for it, and you have to like work for the government for like a couple of years. But it's still a really good opportunity. Cybertractor is still open, yes. I don't have a link to that on hand, but it should be open.
It should be an announcement.
It's also an announcement. Yeah.
Okay, cool. And for everybody who's on CTFD, I've got a flag for you all. And then don't sue me, please. Talk a little bit why that's funny in a bit, maybe. And then for some context, while y'all are typing that in, feel free to talk about this picture. This is a banger tweet by someone named Smia. Smia worked really hard on the Nintendo 3DS. And so that's not the DSi which I'm talking about, but did something similar. Hacked the 3DS, got the homebrew channel, which maybe we'll talk about for a bit, on there, and then took this picture in front of Nintendo's building just to rub it all in. Cool. So let's talk a little bit about what is the DSi. And so show of hands, how many of y'all had a DS or a DSi? 1, 2, 3, 4, about half of us. Cool. I also did, of course. Right on. It's a Nintendo handheld. It's a successor to the DS, Nintendo DS. Actually, there was a Nintendo DS original, then there was a DS Lite, which I had, and then the DSi, which my brother actually had. Anyway, it was released in 2004, so we're going back, way back in time, back before there was any sort of security, which is going to be great for us. So for some more context, the DSi had this home menu, so it could play cartridge games, which you put in the slot, backwards compatible with the Nintendo DS, but also had downloadable content, which put it on the home menu, and it had some built-in system apps, which includes like download play, PictoChat, and what we're going to be looking at, the web browser. So you might ask, why should we hack the Nintendo DSi? What makes it an interesting target? Because it's fun. That is the #1 reason why I hack stuff. Then there's also homebrew. So what homebrew is just running unsigned code. So traditionally, every app that runs on this DSi, every game, must be signed by Nintendo. Actually, I don't know if that's true, because actually the flashcards were pretty crazy. Actually, I might even take that back. I don't know if that's true. I think that might have just been introduced in the 3DS time. But anyway, traditionally, you can run games that are not signed or licensed by Nintendo, which is homebrew. The most popular way of doing this was with flashcards, which is like a cartridge with like a micro SD in it. You can like load ROMs on it and run it. You can dump games from the cartridge slot. You can mod games, you can add cheats, right? Infinite lives, stuff like that. And then of course there's also piracy, which is illegal, so don't do that. But unfortunately, hacking the DSi to allow these other things will introduce the capability for piracy as well. So why did I specifically want to hack the DSi? So remember, I was looking at this last summer, and specifically I wanted to make a really cursed CTF challenge where the flag was like on the Nintendo DSi, and I'm like, give me a URL and I'll visit it from the DSi. And the point was to hack it, like exploit the browser and read the flag. Turns out that was not a good idea 6 months later, because it took me a little bit longer than a weekend. But let's look at our target. So let's hack this DSi. So we're looking at the DSi browser. It's not been previously hacked. So right now, at this point, before I started this, the way to hack a DSi was through the camera app. So what you do is you'd load a corrupted file or a strategically manipulated file onto the SD card, open the camera app, click photos, and it would like parse that, stack buffer overflow, jump to shellcode, and get to your homebrew menu or whatever launcher you want on the DSi. And so there's actually a slight limitation with that. In that if your camera was broken, you couldn't use this method if you hadn't completed the tutorial. Yes? Great question. So homebrew is just a fancy term for running code which you've written or any person has written that isn't by Nintendo. So in other words, you don't most of the time, in order to make a game for the DSi, you have to send it off to Nintendo to like get the stamp on it, put it in a cartridge, and sell it in Walmart, for example. But homebrew is like you put it in a flash card, you yourself can make it. It's using tools the community has made. No need to get Nintendo's verification or approval, and you can just run it on your DSi. Does that kind of make sense? Don't quote me on this, but I feel like it's from like homebrew, like beer or something like that, where you make it at home. I don't know. I feel like that's a thing, but I'd have to Google it for the history. But anyway, that's a great point though. If at any time, just raise your hand with questions. I'd love to answer them as I go along. But yes, so it's not been previously hacked. There's also there's like a drawing app, I think, on the DSi or something like that. Flipnotes, there's an exploit for that. But that was something you have to download to the store. So anyway, there's this very niche market of people which have a broken camera, didn't download Flipnotes, which have technically unhackable DSi's. So let's help them out with the browser exploit. Anyway, the browser was released on 2008, based on Opera 9.5. So Opera is this like ancient browser. It's technically still around, but I think it uses Chromium now. But at the time, they're using their own thing. So it supports some like very ancient JavaScript. Ironically, I tried to use like JavaScript fuzzers on this thing, but it didn't work because the JavaScript it produced was too new. For example, like it's not going to use the let statement. You have to use var because that JavaScript standard is way old. You can't use lambdas. It has to be like function notation. But HTML works, CSS works great. Different image formats work great. Use iframes, stuff like that. We have a huge attack surface. Let's look at like the mitigations. Well, there's literally nothing. There are no mitigations. We can write shellcode to the stack and jump to it, right? A lot of times in these modern systems, stack is not executable. But in this case, it is. Everything is executable, actually. Stack buffer overflows are on the menu. There's no canaries. That would be really great because that's super convenient to just override a return address. Use after frees are trivially easy to exploit, right? What's up, son? So if at any point there's like a write to something we can control, we can write to a function pointer, which we know the address of because there's no randomization. In fact, I don't think there's any virtual memory at all on the DSi. There's no kernel even. It just like it runs it like on bare hardware, which means that an exploitation in the browser gives us a lot of control, right? It's not going to give us everything technically, but it will give us a lot. Okay, and so now that we want to hack the browser, let's look at what resources we have. So obviously I have my Nintendo DSi, but also I have this Melon DS, which is great. It's just like this is the savior. This is the saving grace. This is why it's actually possible to do this now. And it just recently supported, at the time of like I was doing this, it just recently supported emulating Wi-Fi. And beyond that, it just started emulating the DSi home menu. And so now we have the two things together. We have the browser and we have Wi-Fi. Like we're set. We can emulate this all, which is great because I don't have to buy like 16 DSi's to fuzz it at a reasonable frequency. Furthermore, what makes it even better is there was a person who's, I believe, can't remember, I think it's Pro Kion. This was the same person that dumped the BIOS of the Nintendo DSi, which is the boot ROM of the Nintendo DSi, which is dope. Also made a GDB stub, which is something that I can connect to from my computer. So I can GDB remotely into this, remotely, it's on the same computer, but I can GDB into this emulator that's running and look at when it crashes. Yes?
So how does Melon DS, is it like something that, is it like a module, is it like a software? How does it really Wi-Fi in that way?
Really good question. So Melon DS is a software emulator. So it's like an app I can start on my computer. And it pops up like a Nintendo DSi interface. And like the touchscreen is actually me just like clicking the mouse on it. So it's an software-based emulator for the Nintendo DSi. And remember the last part of your question?
How does it emulate Wi-Fi?
How does it emulate Wi-Fi? Great question. I didn't look at the source to understand, but on like some level, the DSi is going to send it's going to have a Wi-Fi chip. And so it's going to use maybe memory mapped IO or some other like IO registers or something to write to that chip. That chip is going to execute the thing, like send the packets, receive the packets, and communicate back to the CPU somehow. And so what the emulator has done is it's going to like catch those writes and reads, like these IO registers or something like that. And then or maybe it's even a higher level of emulation, but basically then it's going to, use the Linux system calls to actually send packets, connect sockets accordingly. So to wrap that, it's going to emulate the Wi-Fi chip. At a very high level, it just emulates the Wi-Fi chip. Kind of make sense? Yeah.
How did you know it was like hardware accurate? Like, how did you know if you could break Melon DS, you could also break the DSi itself?
Really good question. And the answer is that I didn't. The answer is that I was crossing my fingers. And the answer is that it should give me close enough. And then that's actually a great point, because along these, we're going to go even another abstraction level from this and just cross our fingers and hope that it works on the DSi, which we'll get to. Great question. So another thing is that we would love if there was source code or even at least symbols. And so when you're reverse engineering, excuse me, when you're reverse engineering something, if you don't, symbols are just like function names, right? Or variable names or global variable names. And even though you just see the assembly of these functions, you can build like that call stack, or you can see what calls other things. And it's just critical in your understanding of how this thing works, especially if it's within like executing JavaScript. God, it's so complicated. There's so many functions. It'd be great if I could see which one was malloc and which one was free, for example. But we don't get that. We don't even get that at all. And the spoiler is that I will pull the DSi without doing any rev work at all. So that's gonna be really cool. So no browser source or symbols, which is definitely no. All right, so how are we gonna approach this? Let's look to similar approaches. So I'm looking at the DSi, but there's actually been work done on the 3DS, because that's what was popular at the time, like maybe 6 years ago. They're hacking the 3DS browser. And so there's something called validity hacks. And this person here hacked it by sending all the 100,000 layout tests of the WebKit repository. And so a layout test is like an HTML file, which is like, has some text. And then the test is that you execute this HTML file in WebKit, you verify that that text is shown on the browser, right? It's sort of like unit testing or integration testing for WebKit. The intuition is that WebKit has had bugs over the time, which can cause memory corruption or something which is exploitable. And so the intuition is that they've probably inserted regression tests into this suite, such that, you know, if they ever make a mistake again, or, you know, if they ever reintroduce these bugs, these WebKit layout tests will catch them. And so what this person did, Mr. NBA, I'm so sorry to pronounce that wrong, but basically they're going to send HTML files one after another to the 3DS. And is there a crash? If there's a crash, look at exploiting it, because the 3DS uses WebKit. We don't have WebKit. So again, this is the intuition for us is like, well, if it worked for the 3DS, it would maybe work for the DSi, but it's completely separate browsers. But there's still very interesting cases in the WebKit tests. Any questions on that? Yes.
WebKit is the browser for 3DS.
In a way, yes. Okay. Specifically, WebKit is like the underlying framework that the 3DS uses to render the web page. Kind of make sense?
Yeah. Yes, now, and like, how did they do it?
Great question. So the question was, you know, what are some frameworks that browsers are using today, or specifically the DSs, to render things? And so in our case, our Nintendo DSi uses Opera, which is a proprietary web browser, which had its own custom renderer. The 3DS uses WebKit, which is, you know, what we just talked about. The Nintendo Switch also uses WebKit. The PlayStation series, like PlayStation 4 and 5, I know use WebKit. Apple Safari and iOS Safari, those all use WebKit. And so as you can see, finding an exploit in WebKit is critical, because you hack everything, right? With an asterisk, you're not going to have that hack Apple properly because they have a lot of mitigations, but you'll sure hack a 3DS. So, which is great. The way that this is actually hacked a lot of times is 3DS is that millions of dollars of research are put into hacking Safari because there's big payouts, lots of people using it. But as soon as one becomes public, then everybody just like grabs it and hacks a 3DS with it. You know, as soon as all the work goes into hacking Apple, then we just use it for the 3DS. Anyway, we use Opera. Also, the other big one is Chromium, but that's not used on consoles, really. Maybe because it's licensing, I'm not sure. WebKit's open source, also. Okay. And so let's go ahead and do that. So what we're going to do, the plan is that we're going to write a Flash server, which is going to, for every connection request, like, you know, /view, I'm going to return an HTML file. So I can spin up as many emulators as I want. And the emulators, what they're going to do is they're going to send, you know, open them to my web page. That web page has an iframe, which will request a layout test, and then it will just refresh when that layout test is finished rendering, right? So iframe on load, refresh. And it's going to just constantly consume layout tests. Flash server, we can do this in parallel. So that's cool. Here's a video of that. Over the summer, I just had it running on my Huawei laptop. We got 4 emulators here going crazy, consuming layout tests. Gets through 100,000 in about maybe a day or two. That being said, this is a very manual process. Every time it got stuck, because sometimes these things would like redirect, sometimes they would just like hang. I would have to restart the thing. I had no method of automation here. It was just me like looking at it and coming back from work and looking at it and like restarting them when they failed. Very manual process. Anyway, what was the result? So we did get crashes. There were several crashes actually, but none of them to me looked interesting because most of them were null pointer dereferences, which traditionally are not exploitable. You of course have to look at, well, sometimes null pointer dereferences are exploitable. You have to check if you can map the null page, right? So if you can write to addresses close to 0, then you can control maybe the result or the dereference. In our case, that's actually a legitimate possibility because there's no kernel, right? And there's no virtual memory. So we legitimately might be able to write near 0. But then when you look at the memory mapping on the DSi, close to 0 is actually a read-only BIOS, I believe, if I remember correctly. And so in fact, it's not exploitable for us to write arbitrary data there, but we might be able to exploit what is there already. But anyway, it didn't look promising. Yes.
Sorry, I'm thinking 230 right now, so I'm not really that familiar with like the kernel stuff. But
Yeah.
like, I understand that like 0 is like a set register, and like you mentioned something like that. It represents layer 0, you can't really change it. So what are you saying by writing near 0 that you can like, I don't know, somehow like what is that?
Great question. So the question is sort of like, what does writing near 0 mean? And to answer that, a lot of these crashes, a lot of crashes in modern, today, maybe even like when you're writing code for 241 or whatever class, 233 maybe. I'm not sure you do see in that class. But what's going to happen is sometimes you return null from functions, right? Kind of familiar with that idea? That actually is the value 0 in most cases. In almost all cases, it's the value 0. And therefore, if you were to get a pointer from that, and that pointer value is null, and you try to write to that pointer, what you're doing is writing to the address at 0. And that causes a crash most of the time, right? In most modern computers, that will cause a crash. You can't write to null. It's kind of the idea. And when I say close to null, that means writing at like address 4 or address 8. That's pretty close to 0, right? And sometimes you do that because there's like this offset. Like maybe I want the array at index 3, but that array base I think is at null, and so I'm reading close to null because it's gonna be like address 8 or 12 or whatever. Kind of makes sense. In modern systems, that's going to be a problem. It's going to crash because it's not in your virtual memory. Because usually in modern systems, the kernel is going to give you and map you virtual memory. So your pointers are virtual, which means that they correspond to some physical address on the actual RAM, but you don't need to understand that mapping. And when you write to 0, that there's no such mapping to physical memory. In the DSi case, there is no such virtual memory abstraction. The writing to address near 0 is going to correspond to whatever hardware MMIO we've got. We look at the data sheet, or in this case, it's the community run documentation, and it looks like it's going to be a read-only, address range, which has the DS or DSi BIOS on it. Does it kind of make sense? Yeah. So we can't write to it. Lots of kernel exploitation, I think. Maybe in the Switch or 3DS days, you could map virtual memory to address 0, and then you could exploit null pointer dereferences. But in our case, it looks like it's not going to be useful to us. Then there were some other interesting crashes, like we're executing a bad instruction. Those are like great things. That's gonna be like, wow, that's probably a bad problem. Or actually, I don't know if I got one that was that promising. But it was like we're writing to memory, which was like bogus, like completely random bytes. But looking at the layout test that caused it, I have no idea how to map that into something that's exploitable. Sometimes they weren't reproducible. Anyway, it's just a really bad idea. Just reverse engineering something like from that crash, looking at the instructions which caused it, especially with the terrible DSi reversing tools that exist, is going to be near impossible. So here's the breakthrough. The Opera browser is based off of Opera 9.5. Can we find a Windows or Linux build and then hack that? And then see if it hacks the DSi as well. This was like key because not only does Windows and Linux binary reversing tools, not only are they much better, Pwny them, we also have we can use GDB, we can, it's going to be trivially easy. Reversing becomes easier, but still very difficult. And so the answer is, yeah, we're going to go look for that. And so you might have heard Google Foo, wayback-fu is now in. We're going to use the Wayback Machine and look at the Opera website around 2008 or 2007 or whenever the Opera 9.5 was released. The downloads don't work, so I'm disappointed, but they're there. And what we can see is that it redirects it in the URL bar. It's like the file name or something. And so then we can actually use Google for in the modern day to like look for that exact string specifically with those quotes. And we actually find some living FTP mirrors or something. This is like ftp.something.edu, which has this exact file. And so at this point I'm celebrating. I couldn't find a Linux build. I looked. I even used Wayback Machine, and they archived like apt repositories or whatever. And I was so close to getting through it, looking for the build, and at the very end, it didn't have it. Yes.
When you say you were looking for a Linux or Windows build,
Mhm.
do you mean you were looking for like a laptop that ran Opera?
Good question. And so in this context, when I say a Linux or Windows build, I mean an executable file that would run on Linux or Windows. Does that kind of make sense? And so in the Windows case, that'd be a .exe file. In a Linux,
That ran Opera
exactly.
on Windows? Okay.
That itself was the Opera browser. So it's like opera.exe. That's what I'm looking for. In the Linux case, it's going to be, it probably has no extension. But anyway, found a Windows build, which is great. That's good enough for me. And then I could actually, there's a couple entries on Google, so I can cross check, MD5 sum, verify that it's the same file, and I'm not getting like a virus or something. I don't know why they have a virus called this, but there's it. Sorry. All right. So this is the breakthrough, right? Wine. So I'm going to hack on Linux, and I'm going to execute this Opera browser in Wine. And what Wine has is heap debugging tools. And so what that means is when we run Opera through Wine, we can specify to this Wine debug warn plus heap environment variable, such that when Opera runs, every malloc will be set. It will be like it will be set with this constant word. What that means is like, let's look at a free example. So when I free something, traditionally what happens is that nothing changes about that memory. It's just, now I'm gonna know that I can allocate that again later. But with these like heap tools, when I free something, it will actually overwrite 0xFEE, fee, because it sounds like free, I guess, xfee, over every single byte in that chunk, or every single word in that chunk. Such that if there was ever a use after free, then it would try to dereference fee and crash, instead of dereferencing what used to be there, which may be valid memory, and have some like weird non-deterministic crash. Does that kind of make sense? I can draw it on the board if you think that would help. Let's draw it on the board. Okay, cool. All right, so a lot of times here's kind of what happens. So I have my program. Let's do it right here. So I have my program. I call it main. And what this is going to do is malloc some data. So it's going to say, let's say our pointer equals malloc some data. Maybe I'm going to malloc 100 bytes, right? And so over here in our heap, this will make a lot more sense if you take 241. But we're going to say, okay, I'm going to reserve this 100 bytes for you. This is your 100 bytes. And it's going to go and say, okay, well now pointer is pointing to the start of this 100 bytes. That kind of makes sense. The next time I want to invoke malloc, it's going to allocate maybe another 100 bytes. We're going to fill it in here, right? But this is a fixed heap. And so eventually we need to free something, right? And so let's say that in my main function, I'm going to say that the 50th byte, so I'm going to say pointer at 50 equals let's say 100. Usually this is like another pointer or something, but let's say I'm gonna let's not use 100 again. Let's make this like favorite number
25.
25. Okay, yes. Let's make this 25. And so that's gonna say, okay, well this number right here equals 25. Right, it's like halfway in this chunk. That makes sense so far. And then what's gonna happen is I'm gonna, all right, when I'm done using pointer, maybe that's all I need it for. I'm gonna go ahead and free it. Let's free the pointer. And so now our malloc implementation over here is gonna look here and say, okay, now our heap is completely available again. Kind of makes sense, but that 25 value is still there. It's not like I'm going to go and erase this data because that would take CPU cycles, which is inefficient. Great. Now my program over here is going to malloc some new data. I'm going to call it pointer 2. And we're going to allocate like 200 bytes this time, right? And so then I'm going to return like this whole chunk, right? But the point is that this pointer 2 actually has the same value as pointer 1 because this heap was free, right? And so it's going to start allocating it in the front again. And then as soon as I index pointer at 50 again, in sort of an uninitialized way, like right now pointer 50 is uninitialized because I just malloced it. This would give me the value of 25 because that's what was previously there. It just happened to be there. Kind of makes sense. you should never use a variable without initializing the variable. Because whenever you use a variable without initializing it, that's undefined. And in this case, our malloc implementation specifically just happened to be 25. Another valid malloc implementation is me, whenever I free something, I just clear it out with all zeros, then the value will be 0, but that's completely undefined and up to the malloc. Most mallocs don't do that, or free, the heap implementations don't do that because it's inefficient. You don't need it. All programmers should initialize it anyway, right? And so what the wine does is, remember back to the point where we were here, right, with the 100 bytes in the first pointer. When I call free, the wine implementation is going to overwrite this with 0xFEE, all the way across here, right? So that when you allocate a second, allocate over the same region again, that pointer at 25 is going to be hex FE, right? And that's like, oh, FE or FEEE or the whole thing, FE. That clues me in that that was an uninitialized memory access, either by mallocing it, using it, or by freeing it and using it after it was freed. Great question. So here I initialize pointer 2 with the malloc, right? And then I check what pointer 2 at value 50 is. Pointer 2 is initialized.
Pointer 2 and the value is.
Right. Well, let me just say that pointer 2 is initialized with this pointer. That's good. So we can use pointer 2. That's okay. But pointer 2 at 50 has never been set. So pointer 2 at 50 is uninitialized. That kind of makes sense?
Yeah.
And it just has whatever was left over, which usually is whatever was left over. It leads to non-determinism, leads to weird crashes. Maybe nothing happens at all because what was there is valid in the context of this program. But we want it to crash deterministically. And so we fill everything in with this sentinel value. Yeah.
And so if any of us were programming a DSi, in order to stop this from happening, you would set your stuff to null after you free it.
Great question. Yes. So the answer to stop this from happening is that more generally, how do you stop use after freeze? And if you set everything to null after you free it, well then this thing would just get 0, which may also cause a crash, right? The point is that it's uninitialized and undefined. And so what you want to do to prevent this sort of problem from happening is before you use pointer 2 at 50, after a malloc, you need to set it to something that you know, right here. So if I wanted to
Like
be
all zeros or something.
sure, exactly. The point is like you cannot use uninitialized variables, and you cannot use variables after you free them. Okay, that's kind of the key. And so as long as you are like writing, as long as you use malloc and then you initialize it and then you use it, you're good. And as long as you free it and then never touch it again, you're good. Because writing into it after you free it is bad. Reading from it after you free it is bad. Yeah. Right. So those are two cases you can avoid. Yeah.
So when you free, it's not actually deleting the memory,
It's still there. It's still there for the malloc to give it to someone else.
you're just not allowing the function to access it. What does free do then?
What does free do? Okay, sure. Let's take a little bit. We're probably gonna spend a little more time on this because this is again a 241 question. But free. So malloc, when I request, let's do a new one here. When I request 100 bytes, it's gonna malloc is gonna say, okay, here's your pointer. That's what it's gonna return. When I request another 100 bytes, it's gonna say, here's your pointer. I'll give you that one. Okay, I'm gonna request another 100 bytes. It's gonna say here's your pointer. And now I'm gonna free 100 bytes. Or I'm gonna free the pointer. I'm gonna free the second pointer. Or I'm gonna free the second pointer. And so what it's gonna do is mark this as free. This is used. This is used, right? So you're gonna mark that one as free, but it's not gonna overwrite anything in it. And it's not gonna prevent anybody from reading from this area of memory. It just knows that it's free, so that when someone else requests 100 bytes, it can give it this memory instead of keeping that going, right? Kind of make sense? So in other words, when I free something, the memory that's behind it is still there, unchanged, but just should not be accessed. It can be accessed, but it shouldn't be. And when it is, we get what we're gonna do. We're gonna hack the thing. Hopefully that helps. Definitely it's gonna make more sense after CS241. Cool, let's move on. So anyway, we're gonna go run through the layout test again. And so it turns out one of those layout tests is going to crash on a read access to hex VP. And so from what I just said, this indicates that somebody freed memory and then tried to access that memory that was backed by that original malloc again, right? And that's a use after free, which if you were at Pwn 4, I believe, was a little touched on briefly. And so what I originally thought was a null dereference happen to be a use after free. And like, why does that happen? Because originally, remember that it's just going to access whatever was there, which happened to be a null pointer, or just the value 0 when the DSi was doing its thing. But when I turn on this heap thing, well, it turns out the value is not 0, but more generally, it's whatever was there. And we're going to go ahead and try to see if we can write whatever we want to that value. Okay, so here's the bug. It's actually kind of hard to see on this projector. But what's actually happening here is that I'm going to insert a CSS rule, I guess. The point is that in this like whole exploitation process, only know what you need to know. Like again, I've never reversed anything at this point. All I know is that it's reading from a freed memory. That's all you need to know to hack this thing, right? In this case, it's putting something in, question mark, is a CSS value? I don't know. Anyway, it succeeds. And so now naturally the length of the CSS rules, because I've inserted one, it has value 1. That makes sense, right? Insert 1, value 1, good. And then there's this try catch block, and this insert rule with this specific rule, I don't know what it does, it's a layout test, right? It's going to actually throw an exception, a JavaScript exception, and I'm going to catch it in this block. Everything is working as intended, because for some reason, this thing here should throw in a JavaScript exception. You should be able to catch it here. Everything is good with that. But then, after that, we expect their length to be 1 still, because it failed to insert. But what actually happened is that the length is 2. Something is very, very sus here, right? Because we failed to insert it, yet it seems to have been inserted. And then when we refresh the page, we get this like use after free read. Something is really weird here. So at this point, if we had source code, we would look at the source code and we would like set breakpoints. We would like look at the stack trace. We would, whatever. And then, oh, well, okay. Well, then in this case, oops, every time we do this, oh, at media, it turns out that this is free. Oh, we got to split it this way. We don't have any of that. We don't have any of that. We don't need to do that. We only need to know what we need to know. And so at this point, we need to overwrite that freed stuff with something we control. And preferably we'd like to not read the thing. We'd like to write to Fifi. And we'd like to jump to Fifi. And that's what we're going to do. We're going to guess God our way to victory. And we're going to just go ahead and play around with those corrupted objects and like observe the results and choose the one which is easiest for us to exploit without any reversing. So it just so happens after we insert those rules, such that we're in like this weird pseudo state where there are 2 things when there should only be 1, we go ahead and delete the 2 things which are there, which really again should only be 1. And just by like finagling and like guess-godding my way to victory, it turns out that when you access the length, because I'm curious what the length is after I delete 2 things, right, on this corrupted thing. Well, when you access the length, it's going to jump to Fifi. And that's how we know we win, right? Jumping to Fifi is like, that's at this point, we're like, we can win this. We can hack the thing. Because you replace Fifi with your address of your shellcode and you win. We know where the shellcode is. We can jump to it because there's no mitigations. All right, we definitely have a hack here. And so why does the link jump to Fifi? It's a little bit technical, but it's probably because of like v-pointer stuff. So you have a v table on this like JavaScript value. Accessing the link is like .get value, and that because we're like that JavaScript object is probably on our freed memory. That v pointer is also going to be on our that v table is probably also going to be in our freed memory. Accessing it, jump to Fifi. But again, that's all like hypothetical. Probably, I don't care to reverse it and understand why. But all we know is we're jumping to Fifi. So let's go ahead and control the jump. And so we can use GDB to find the size of the malloc chunk. Basically, on crash, it's going to put us into GDB, and we just go ahead and look at like the heap metadata, which we just again guess God that it exists, because that's often how heap allocators are written, which is pretty interesting. It's not how it works on the 3DS, but we'll talk about that obviously at a different meeting. So anyway, we know how big the thing is. The goal is that we're going to spread the JavaScripts of the same size to regain that Fifi and write arbitrary things. In modern exploits, use like float32 array or some like uint8 buffer or something like that to just like trivially allocate an object of a certain size. But we don't have that because this is browser ancient. And so again, we look to like other exploits of the day. There's this exploit called str2x, and it uses canvas objects to allocate fixed size things. And so let's do that. We're going to create like 100 or 1,000, I can't remember, canvases, which is just an HTML element, right? And then we're going to set their width to the malloc size over 4, because each pixel in a canvas is 4 bytes. And then the height's going to be 1, so that we specifically allocate exactly hex 50 bytes. And then we're going to go ahead and fill the RGBA values of that canvas object with hex 414141, just as a value to know if we got a crash, right? And then we're literally like guess binary search. I don't know, just like guess how many canvases. Again, guess God, because I'm not reversing this thing. And it turns out after, online, this amount of canvases is actually going to get us to jump to dereference EAX. And the EAX is going to be 414. So now it's official. We can control where we're jumping to. Now we just got to jump to some shellcode, right? So at this point, I move on to the DSi because it doesn't make sense for me to fully exploit the wine like the upper browser. It would be cool though, because then you have like a 0-day for like a real life browser which existed, but it's like from 2007, no one really used it, 2008. But this is the type of stuff that like governments have, right? It's like a browser which with a website which you go to which exploits your browser, which I just thought was cool. And like this is like the tech of the day in 2008. I mean, this is what governments were doing, right? They had websites like this, which just use these kind of things. There's no mitigations, man. it used to be this easy. Anyway, so the key to this is that we're going to create an op sled because there's no ASLR, but there is that like heap non-determinism. So we're just going to make a big op sled and put a nop in there, and then put our shellcode at the end of that. So that would jump to somewhere which is probably an op sled, somewhere in the middle of our op sled maybe. It's going to execute those nops, slide all the way down to our shellcode. This is like hacking like it's like 1999. And we're going to go ahead and do that. We get a pretty fairly consistent address. So we're going to go ahead and spray the address of what we think our shellcode, our op sled is going to land at. And that's going to work fairly consistently, like 1 and 2, 1 and 4 maybe. I mean, it's good enough because I really just wanted a proof of concept. So what shellcode should we use? The DSi has been hacked before, right? With those camera payloads, those flip note payloads. There's this thing called mini TWL payload, which just loads something from the SD card and executes it. And so we can put anything on our SD card and it will just load it and execute it. So most of the time, boot.nds is going to be like your second stage launcher. In my case, I use Twilight menu, something community made. But it could be like a graphical like haha hacked by Nate or something. Maybe I should have done that, but I was too lazy. It had been a long time at this point. But yeah, it's hacked. Here's a quick demonstration of it. Just in the last bit of the exploit, flashy colors, part of the mini payload. It's gonna reboot into your boot.nds, which in my case was Twilight menu. So there you go. You go to the website, hacks your DSi. I mean, it does what it says. Cool. So some takeaways from this. It's not well suited for CTF shell because it took longer than a weekend. I actually worked like all summer on this. But I definitely think that if I would revisit it, I could do it so much faster based on what I learned. If you want, basically the big takeaway from this is like if you want to find heap problems, which is like most common in web browsers, you need to have like heap debugging tools. You need to be able to fill the malloc and free chunks with something. Otherwise, you're going to be completely non-deterministic. You won't know if you're exploiting it correctly. I mean, that was just critical. That was just critical. Debugging was like fine. You can have like a terrible debugger to make your exploit. But bug hunting, you need to get those heap crashes. But the point is like you can do this too. All these techniques are from Pwn 1 through 4. We got the jump to shellcode. We've got the use after free from Pwn 4. Yeah, I mean, absolutely. There's nothing here that I used that was like high tech. So I literally didn't reverse anything. So I exploited this entire thing without reversing anything. I think the point is like you need to be satisfied in knowing what you need to know and nothing else. That was the name of the game. Otherwise, you get overwhelmed in the complexity of like the size of this DSi binary that has no symbols. It can be intimidating, but you don't even need to reverse it. It just works. The more mitigations you have, the more reversing you'll need to do though to get things to work. I literally just had time and willpower, which is cool. So what's next for me? The 3DS browser will get hacked soon. Like, I guarantee it. We've got great crashes now. Basically, I've been working the last like 4 weeks, like last month or so. Maybe it's for longer. I don't know. Really hard in getting the 3DS browser to be hacked, and that one's has a lot more to talk about, including like a completely automated fuzzing setup, and much more complicated bugs, and my own malloc and free patching. That's pretty neat. It also has more mitigations, but not a whole lot. So then I'm also going to be looking at the switch next. I got 2 ready to be hacked. I'm going to do the hard to see if we can voltage glitch the bootloader. And then I might look at the browser and the kernel at a later date. But shout out to my brother Matthew for letting me use his DSi and his 3DS. Couldn't have done it without him, literally. And Anisha Nankar for believing in me. But yeah. Thank you. Are there any questions?
You were like writing of the exploit. How did you compile it for the device itself?
Good question. So writing code for the exploit, do you mean like the shellcode?
Yeah, or like writing like sort of like some of the exploit.
Oh, great question. So let's maybe start with the code that I wrote from the top. So the code that I wrote would have been like the JavaScript, which was running to initially set up the heap, and then to overflow, like to overwrite the freed value with something that I control. So that's going to be in HTML and JavaScript, which is like the same across all devices, which has made it really nice in that regard. The only thing that would have been DSi specific was going to be the addresses which I wrote and the shellcode which I wrote to the heap. And so the addresses I found using a debugger. So I'm like, okay, well, it most often allocates my NOP-SLED at this address. Let's just assume it always allocates at this address, write it into my JavaScript. Then the shellcode, I didn't write. Actually, I did write. No, I didn't write it. There's something called mini TWL payload that I linked here. What that is a collection of like C files, which will like initialize the file system on the SD card and load it and jump it, etc. So it's in C. But then there's a tool chain which exists for the Nintendo DSi, which you give it a make, you have your make file, it will compile all the C files down into like an NDS file or an ELF file actually first. And then what I do is I use obj copy, and I can copy out the code, binary, like the actual like bytes of that code from the ELF file, and I put it into like a .bin file, which is like my shellcode. But all I really had to do was like the obj copy stuff. And it turns out that ARM is pretty like position independent, and so it kind of just worked. Does that kind of make sense?
Yeah.
Cool. Right on. That's a good question. Any other questions? Okay, right on. Does someone want to talk about the next meetings? I can just run them down real quick if you want. Okay, done. So this Thursday, quantum computation with George. Sounds sick. Next Saturday is scavenger hunt, don't forget. And then the next Sunday is fuzzing with Richard and Juniper. That sounds dope. Got them right here with us, so it's gonna be cool. Yeah, that wraps it up. Thanks for coming. If you do have time, I have actually one more interesting tidbit trivia, low effects trivia, which I thought was cool, but I didn't necessarily have time to talk about. Y'all can leave, of course, whenever, but essentially when I wrote, so that NOP-SLED, where's the NOP-SLED at? Here it is. And so actually when I put on the DSi, it turns out that like 50% of the time it works. It will dereference the first like 4 bytes of the canvas or that freed memory and jump to it. And the other 50% of the time, it like does a double dereference and then jumps to that. So I don't really know why that happens. Again, I don't care to know why that happens, but it turns out we can do this very clever thing to make it work for both cases. How can we do that? This NOP value is actually the address of the shellcode. So that's pretty crazy, right? It's almost self-referential in a way. It turns out in ARM, there are like hella NOPs. Like there are like, I don't know what % of the instructions are effectively NOPs. Especially for like my case where I don't need registers to be certain values, right? Because in our shellcode, you can just set them up however you want. And what that means is that consider the first case where it jumps to this address. Well, then it executes these as NOPs and slides down to our shellcode, no problem. Now consider the case where it does 2 dereferences. So the first thing it does is going to it's going to dereference our address. So okay, now it's looking at the NOP-SLED. And then it's going to dereference what's in that NOP-SLED and jump there. And the address that's there is the address of the NOP-SLED itself, which also functions as a NOP. So it just jumps right back to where it is, continues executing, it still works. So again, I don't know why it happens. I don't care to know why it happens. I just do. Yeah.
You just get really lucky that the address you wanted to like exploit was also a NOP.
Yeah. Yeah, and I don't know how to like quantify that luck because it seems actually kind of probable, right? And so, and furthermore, that NOP-SLED is actually quite large. And so I could sort of like finagle maybe like somewhere in the NOP-SLED an offset, which is like effectively a NOP enough for me. So it doesn't have to be this exact place necessarily, but I just like chose a place in the NOP sled, like, disassembled it. It's not enough for me because maybe it like adds the two registers together, which technically isn't a no operation, but in my case, doesn't have any side effects like writing to memory or jumping somewhere. So it's good enough for me. Yeah.
So not is null version.
Right. So a NOP stands for no operation, which is an instruction which literally does nothing. And that's what it means literally. In my case, I call it like an effective no operation, effective NOP, I guess, where maybe it multiplies two registers together and saves them in a third register or something. Right. So like more generally, like why does that instruction exist? Or why in my case do I want to use it?
Yeah.
And both?
Why does it exist?
Why does it exist? I don't actually know the answer to that question. It could be used for like timing reasons, maybe. Like you want to like, maybe you. So a lot of times, like maybe you want to pad out your instructions to like alignment. I've seen that before. Maybe you want to like stall a couple cycles. Maybe. I don't really know why you'd use it in practice, but in almost all instruction sets it exists.
If he uses all of the above.
Nice. Let's go.
It could also be that they reserve those instructions so that way we add maybe big newer CPUs, so like they can just use those no ops, reserved no ops for their own new instructions.
Cool. And so the reason I want to use it in this particular thing is because here's actually kind of what happens is like we have this heap here, right? And then this is going to be like, it's going to free this chunk. And then I'm going to have my bad address here. Like here's where the shellcode is, right? All our nice 4.1s. And then so it turns out that I've allocated this address 41414141 or whatever here. Here I'm going to have a lot of no ops. That's going to be a lot of no ops. And then here's actually my shellcode. Right. And the point is that I don't know if this is going to be allocated at 4141 every time. It might be allocated here, it might be allocated a little bit later, it might be allocated a little bit before. The point is that if I always jump to a constant address, I'll land somewhere in our NOP sled. Maybe I'll land here, maybe I'll land here, maybe I'll land here. But the point is that if I start executing here, it's just going to execute NOP after NOP after NOP after NOP. It doesn't do anything. Okay, shellcode. Then it's going to go and execute my shellcode, which actually does something. And no matter where in the NOP sled that I land, it will always slide down to my shellcode and execute. It adds reliability to my exploit. That makes sense?
So basically it jumps within a certain range of value, so you just make sure like if you jump within this range of value, they're just good.
Yes, exactly. Yes. And because the heap is non-deterministic, so this like chunk that I allocate, remember here, I'm allocating the
it'll
NOPs.
jump to a random location, but it'll jump to a random location within the range.
Yes, that's the idea. And then I think with 50% probability or something, maybe it's even less, it's kind of unreliable exploit, it will land in my NOP sled. Yeah. Sometimes it lands like out here and it would cause just a crash. And then you just like try again. And then that's why these, when you hear like exploits working with some probability, that's why it happens. Because like heap non-determinism, maybe ASLR. That's kind of what's up. Good questions. Cool. I think that wraps it up. Thanks for coming. Yes.